Okay. This is our last set of notes in Physics 20, guys. Isn't that kind of exciting? Last set of notes in Physics 20. So, reminder then, just so everybody's clear, we've got basically today, tomorrow, Friday is kind of some work time. Finish up your lab, finish up your assignment, work on that sort of stuff, and then, totally blurring right into this. Then next week, at some point, write a quiz, write a unit test, and then we're good to go for Christmas. If I need to mark something, can we, I think a few of us have had a chat here and there where we need to, but can you make sure to let me know if I'm expecting to mark something that's late? Because I'd sure love to know what that is before Christmas and then get it marked over the Christmas break so that it's done with by January. Okay, let's talk about power. So my first slide here is just kind of talking about how power is actually a word that gets used so much in our everyday vocabulary, and it has so many different meanings. Not that I need you to know all these from physics, but power is a measure of strength, right? I could talk about that I'm a very powerful person when I'm fighting or something, right? When you're an athlete, maybe you're very powerful. Right? Power has meaning and influence. We probably talk about power in social studies. How Donald Trump now would be a very powerful person because of the influence he'll have as president, right? In terms of his the connections he'll be able to make. Military, they have power, authority. In a way, I kind of have a little bit of power over you as being the authority in the classroom. Well, I don't really necessarily use that sort of terminology, but people would refer to that as a type of power. The last one I threw on there, we use the word power in math. Right? A power would be an exponent. So, but none of those really matter, so I guess ignore what I just said for the last minute. I'm not testing you on that. In physics, power is defined as, you can highlight this if you want. Power is the rate at which work is done. In a way, think of power as a speed. It's not actually speed, but think of it in your mind as speed, because speed is really a distance over time. Right? Speed is how far you go per time. Power is very similar, only it's how much work you do per time. Does that make sense? And so, maybe one way of approaching it is from your work sort of view. Your job, your boss gives you a job and says, I want you to clean this floor. Right? Now, if you do that amount of work in 5 minutes, that's a lot of power. If you do that work in 9 hours and you really dilly-dally and take your time, then you didn't use as much power. Does that make sense? So power is about how much you can accomplish in an amount of time. So there's actually kind of two formulas I have here. I'll just skip back here. One, this is the one on your formula sheet, I believe. Power is work over time. How much can you get accomplished in a certain amount of time? But you know how work is really energy, basically? That's the definition of work and energy. So you could also make it how much energy you've expended over time. Does that make sense? Okay. I'm going to go back to that first slide real quick and just point out two of my notes here. So the first note I've already mentioned, power is a rate of change in a similar way to velocity. Anything that is like a something over time would be considered a rate of change. Okay, that's like an overall term we use. And the second note is actually where we use it. If you guys have actually taken calculus with me, that's actually a big part of what calculus is about, is how things change over time. For example, if I asked you to compare how your bank account changed over time, there's like huge overlap with economics, because I would sure like to have a high degree of money increase per time. Does that make sense? If I told you that you were going to make $100, you'd be like, sweet. But if I told you you were going to make that $100 over 50 years, less sweet. But if I told you you were going to make $100 in the next 12 seconds, yeah, that's even better. You know what I'm saying there? So sometimes the speed at which things occur, not necessarily speed like true velocity, right? But like how fast they occur per time, that's very important. So anyways, just so you're aware, anytime we have like a per time, a rate of change, that has huge calculus implications. So you will see these sorts of things come up again in calc. Okay, I'm going to show you two examples, and I think that should be enough actually to get you going, because it's a very straightforward formula. It's just two examples, right? Okay, so here's our first one. Oh, I didn't even talk about it. The unit for power is in watts, named after James Watt. Sometimes you'll hear it as a kilowatt, which is just a lot of power, 10 to the 3. Okay, so the unit is watts. So with that, if I give you a 150 watt light bulb, that is telling you a power output. Does that make sense? It's telling you how much energy is being expended per second. Wouldn't that make sense though? That you should measure like a light bulb in energy per second rather than just energy total, right? Because it really depends on how long your light bulbs are on for. If you turn your lights off all the time, well then it's not expending nearly as much energy, right? So we want to measure it as like a per second thing. So anyways, power is equal to how much work, or I guess how much energy you've got per unit of time. In terms of units though, watt is the normal unit that we use for power. Let's just call this change in energy. But this 2.5 hours here, we're gonna have to convert that, right? So 2.5 hours will be what? 2.5 times 60 times 60 to get into seconds? 9,000? Thank you. Go ahead. 150 watts times by 9,000 seconds. That should tell you how many joules it is. What's 150 times 9,000? 1,350,000. That number? Cool. Okay. Unit then would be energy is measured in either joules or in Newton meters. Why don't we take a second though to talk about units here? Let's finish off the question. This will be 1.4 times 10 to the 6 joules. You guys okay with the math part of it? Okay, let's talk about units then. If a watt is equal to a joule per second, right? Because the energy, the unit for work was in joules, and the unit for time was in seconds. Let's break that down a little bit further, because they love to test on us in diploma. What is a joule made up of? Okay, let's go with Newton meters, so that'll work. Newton meters per second. What is a Newton made up of? What is a Newton a measure of? Kilograms meters per second squared. The reason why is that a Newton is a force. A force is a mass times an acceleration. So this would be your Newton. This would be your meters over that second there. Let's put it all together then. What would the totalness of the watt unit be when we're done then? So you have kilograms. Meters squared. Yep. There. Those are kind of the broken down base units of a watt. Let's follow that one more time. A watt was a joules per second, right? We had that on the previous slide here. It's joules per second. A joule is a Newton meter, still per second. A Newton is a measure of force, that is a mass times an acceleration. So really this meters then becomes squared. When you divide it by an extra seconds, now it becomes a cubed second. So that is the unit of watts. That's what 1 watt is equal to. One more thought. You know how, maybe you've heard this before, sometimes you hear a unit called a kilowatt hour. Ever heard that before? Sometimes appliances, when you go buy a new one, they'll say that this has a rating of 100 kilowatt hours. In a way, it's actually not measuring wattage anymore. It's now back to measuring energy. If I were to give you a unit of, say, kilowatt, and then I re-times it by hours, what's really happening is in the power formula, how it was like work or, let's say, energy over time. Rather than measuring energy straight up in joules, another unit for it would be like a watt times an hour. Because what you're going to do is you're going to take time over here, and you're going to multiply it by power. See how power is measured in watts? Well, except they just put it in kilowatts. And if you times it by time, although time is normally measured in seconds, they'll convert it into hours. So if you ever see the unit kilowatt hours, it's actually not a unit of power. It's actually a unit of energy again. Just it's a strange concept for how you do that. Convert the watts into kilos and convert time into hours. Anyways. Sound good? Okay. One last example. You have a 200-watt motor. It is trying to lift shingles to the top of a roof at a constant velocity. One pack of shingles is 28 kilograms for mass. We want to figure out its velocity. Before we solve this question, we might not hurt to draw a bit of a picture just to figure out what's happening here. So, I mean, oh, yes. Oh, it just died on you. Okay, let's see what we can do here. Okay, I'm going to start a new one. We'll see what we can do here. Huh. It actually says I'm not connected to a server anymore. This is unfortunate. We have like one example left and it decides to kick us out. Close the program. Just close it. Stupid thing. Okay, I sent another meeting possibility. Let me know if that shows up for you. You can see it? Shoot. It may just be easiest at this point for me just to point the computer at the screen for one last example. Why don't we just do that? Because it's one example here. Let me just move the laptop so you can just see what we're doing here. Otherwise, we're just wasting time probably. Okay. How's that? Reasonable? Okay. Okay. Cancel. Okay, back to this one. So, in terms of this one here, what we're looking to do is you've got these shingles that are 28 kilograms, and we're going to be pulling them upwards with a motor. I don't know, I imagine some sort of torque where it's pulling at a constant speed. I don't know, some sort of winch that's pulling them upwards. It's going to be applying some sort of force, is it not? It's going to be applying some sort of applied force. What force does that actually have to overcome, though? Yeah, gravity, right? So hopefully you'd agree here that the applied force of the motor, I'll even write this out in words, the applied force of the motor needs to equal the force of gravity. Well, remember how Newton's first law, an object in motion will stay in motion, right? So long as it's already in motion, so long as all it does is it just counters gravity, if it is currently in motion, it should just remain in motion. So I'd agree with you that right off the bat, it has to be a little bit more to get it going, right? But after that, so long as the motor applies just enough force to counter gravity, it should actually just remain in motion on the way up with a nice constant velocity, right? So if it was more, then this thing would accelerate, but we're going to make it just enough just to keep it in motion. So let's make the applied force equal to the force of gravity, which means that our force is going to be equal to m times g, which will be 28 times 9.81. Just kind of leave that sitting there. That is how much applied force we need to have. That much. A little bit more probably to get it going. But then once we get it going, then so long as that's the applied force, then it will continue raising upwards according to Newton's laws of inertia. What's the formula for power? Well, power was equal to your work done over time, for example. I want to show you a little trick though that sometimes comes up here. You know how I was playing around with formulas? This is another skill that we're going to use a little bit more in Physics 30. I'm going to break apart work into work being force times distance, because work is force times distance. You know how it asked me for a velocity? If it kind of seemed odd to be like, where are we going to get a velocity from? Right there. Do you see it? What is velocity equal to? Distance over time. So this is another example of kind of how you have to take formulas and manipulate them a little bit. In a way, if work is force times distance, but velocity is distance over time, we can write a new formula. Power is force times velocity. Can you see how that fits in there? It's sneaky how that kind of works there, where we had to take a formula, and it wasn't just substitute another formula in. First we had to like take one of the formulas kind of apart a little bit, rearrange it, and then recognize, hey, d over t, that's velocity. Now it's actually really straightforward though. The power was given to us, wasn't it? It was 200 watts. The amount of force we're going to require will be just enough to overcome gravity, which will be 28 times 9.81. That should tell us at what velocity is traveling. So you just have to divide by the 28 and 9.81. Let's get a speed. 0.73. 0.73? Okay. We've done this before in our dynamics unit. I'm thinking of examples where sometimes I would say a biker is biking up a hill with a constant velocity. And in that section there, it kind of implied to you that if the velocity was 0, then it means that, or a constant velocity meant that there was no acceleration, so that you knew that the two forces were equal to each other. We're kind of working backwards from that here. We're saying we know there is no acceleration, therefore, as these things are moving right here, we know the acceleration is equal to 0, and based on that, your applied force better equal your force of gravity. And that's kind of how it got us started. But hopefully you guys all saw the little trick here. This little twist, pull work apart into force times distance, which is what I wrote down here. Distance over time gives us velocity. Sneaky, eh? So that's kind of the first one of those that we'll see. We'll do this a lot more, that sort of skill, when we get to like the magnetism unit and the electric unit in Physics 20, where you have to take a formula, pull it apart, and be like, hey, I can fit this one into there somehow. So anyways, here's my lesson. Is there any questions on power? So I guess two main things to know. One, I'd like you to know all the units for how it works. So the unit is now a watt, which can be made up of kilograms and meters and seconds. Only now it's like, what was it? Kilograms, meters squared over seconds cubed, I think it was. And then just be aware of the fact that a power is basically how fast you are doing your work. Right? And so if someone is really lazy and they accomplish their goal, but they finish it in 10 hours versus someone who finishes it in 1 hour, that's a good way of thinking of power, right? How much energy did you expend per second? Okay. Okay, let me stop the recording here, but I do want to talk a bit about your lab for a bit if we could. So.